Section 7.4, Inverse Laplace Transform. So in the previous sections, we were given a function which was continuous on 0 to infinity, and we found the Laplace transform of that function. We noticed that there were few functions for which we were able to find Laplace transform. In the same way, now if we are given a Laplace transform, we can find the inverse Laplace transform, little f of t. Inverse Laplace transform also satisfies the linearity property, same as the Laplace transform. So let's look at this example. We are given a function big F of s. Often you will have to first manipulate or rewrite the function in a way that you can easily see the inverse Laplace transform. In the first case, in this example, the only thing you might do, and in the later examples you will see that you don't need to do this step even, you might write 6 times 1 over s minus 1 over s minus 8 plus 4 times 1 over s minus 3. Now, from here we can see that 6 I keep here, and 1 over s is the Laplace transform of 1. So I can just leave it as it is, minus, the 1 over s minus 8 is e to the 8t plus 4 e to the 3t. So that's it. That is the inverse Laplace transform. Second example. So now again, let's see, we might have to manipulate it. So the first term is fine, is similar to that one. So if I want to write the f of t, for the first term, it will be just 12 times e to the, now if I had an s minus 2, it will be t to the 2t, but now it's s plus 2, so it will be e to the minus 2t. What about the next term? So 1 over 3s minus 5. We haven't seen a factor like that in the bottom in the Laplace transforms, but notice we can factor out the 3 at the bottom, and this becomes s minus 5/3. So I can write my function like that. So the first one is 12 over s plus 2 minus 1 over 3 times 1 over s minus 5/3. Now the last term, 7 over s to the 5. For that, you have to recall that the function t to the n, the Laplace transform of t to the n was n factorial divided by s to the n plus 1. So whenever you have an s at the bottom and raised to some power, more than 1, power greater than 1, then this is the inverse Laplace transform of t to the n. So that since we have 5 as a power of s, it means our n is 1 less than 5. So our power n will be 4, and 4 factorial goes in the numerator. We already have a 7, which I'm going to put on the side. But then if I multiply the numerator by 4, I have to put a 4 factorial in the denominator as well. And I have s to the 5. Now when I come here, so second term is going to be 1 over 3 e to the 5/3 t plus 7 over 4 factorial is 24. 7 over 24 times this quantity here is the inverse Laplace transform of that one is just e to the 4. looking at the next one, 6s over s squared plus 25. So I can rewrite this one as 6 times s over s squared plus 25. Do we have any function whose transform looks like this? If you recall, cosine function. So this will be the inverse Laplace transform of this one will be cosine 5t. What about the next one? So I can put the 3 here, and then I'm left with 1 over s squared plus 25. Now, if I put a 1 here, then that is not a Laplace transform of any function. But if I have a 5 there, that will make sense. So I'll put a 5 here, but then I have to put the 5 at the bottom as well. So now I can take the inverse Laplace transform. So little f of t will be 6 times cosine 5t plus 3 over 5 times sine 5t. So that's it. Now these were pretty simple examples. We are now going to get into a little complicated and then a little more complicated ones in the next videos.